All right, good afternoon, everybody. This is going to be a session Docker for developers. We're going to listen to Nelson and Tony from Splunk talking about their journey as far as taking a monolith and containerizing and how they got from here to where they're at right now. They're going to be available for a few minutes after the session to answer any questions, and if needed, I believe they can stay a little bit longer. So let's get started. Thank you.
All right, thanks for the intro. Welcome, everyone. Thanks for coming to our talk. Today, we'll be talking about how we packaged our monolithic software, Splunk Enterprise. So before we get started, I'm Tony. I've been working at Splunk for about 3 years as a software engineer in infrastructure group.
My name is Nelson. I'm a senior software engineer at Splunk. I've been at Splunk for about 3.5 years, also working on engineering infrastructure.
So today's agenda, we're going to start with why we had to go on this journey, what was our problem, and what was our approach to the problem we've been having, and how did it work out, and what is the next step for us. So we work for Splunk. At Splunk, we are committed to make machine data accessible to everybody. We help our customers aggregate, analyze, and really make sense of the data, big data that they have, and tap into the value of the sheer volume and the variety of the data that they have in their operations. Our core software is a Splunk Enterprise, which is a very powerful platform for data ingestion and aggregation and analyzing. It's actually written in C++ and Python and cross-compiled into more than 10 operating systems and multiple chipsets. It can be deployed as a standalone or a distributed mode with multiple roles. But really the point is it comes down to a single binary. All the logic, all the application logic is in a single binary that you can take and install. Which is a common characteristic of a monolithic software. But to me, it feels like taking a Splunk and installing in a distributed manner feels like building something like this, right? Imagine dragging all these stones up the hill, and you have to set it up right. You have to put the angles and you see the stones on top of the stones, right? It's very complicated steps. And deploying Splunk in distributed mode has been building something like this. But if you can set this up once and go home, it's not too bad, right? But we're engineers and we build software, we build product. Oftentimes in the development process, you write code, you build a binary, you deploy it, you test it, tear it down, iterate over and over again during the deployment process. So imagine you have to build something like this for over thousands of times during your development cycle. So we needed a really reliable and consistent way of repeating these processes inside of the company. So we started exploring about 3 years ago, and we wanted to be at the land of microservice. We knew that turning our monolithic software into more of a microservice architecture would allow us to scale better, efficiently control and manage our softwares internally for our customers as well. But really, it's not really a simple journey. So taking a monolith to a microservice is not that simple. First, it's time intensive. You have to break down your software to the point where you can deploy it, and that time is very expensive, and you don't see the ROI right away until that time comes. And very disruptive, right? You are breaking down a software. For us, we're breaking down a software that we've been building over 10 years in different languages. So that itself is a very heavy engineering task, and then we don't know what we're getting ourselves into, right? And at the end, it's also costly because all those engineering man hours. As a company, we are all competing in a very fierce market, and investing resources to do these kind of operations might put your business behind the competitive horizon. So you always have to think about, it's critical to think about each step of this migration to the better world, to the better microservice architecture. So who are you going to call, right? Why are we talking about this? What's our role in all of this? So we've been running Splunk in a containerized environment for over 3 years internally. And we heavily utilize containerized infrastructure to efficiently scale our development and testing environment. And infrastructure group at Splunk has been working hard to be always step ahead of the product engineers, because we are the ones that's paving the road, making sure the tools and the environment that the product engineers need are there when they get to the next level. So at this point, I'm going to hand it over to Nelson to talk about what we did in our journey.
Cool. Thank you, Tony. So I'll be talking about our containerization path, how we got to where we are now. And for us, it really starts by taking that first step, building that first Docker file. You can see here, we started out by taking a convenient operating system image from Docker Hub, Debian Jesse in this case. We added a couple environment variables inside of this Docker file to suggest and determine what Splunk product as well as what Splunk version gets baked into this Docker image itself. After that, slap a couple run commands in to install your dependencies, fetch the distribution you want, install it, mount a couple volumes, add an entry point which starts your product. After this, you're pretty much good to go. All right, thank you everyone for our talk. We'll be outside if you have any other questions. No, obviously, it's never that easy, as always, and we always wish it was that simple. We wouldn't be here if that was the case. So in defining our containerization strategy, we actually took a step back to determine what was it we actually wanted to achieve. For us, it made sense to split requirements down on the application side as well as the scheduler side. We knew that having run Swarm and Kubernetes internally, we wanted to make sure that our image was scheduler agnostic and not tied to the specific constructs of each of those orchestration platforms. On the application requirements, these are really what we mapped to end user expectations. It was paramount to us that the Splunk image was accessible to our end users. We wanted Splunk running in containers to feel familiar to our existing user base, as well as lowering that barrier to entry for any new users. Splunk had to be adaptable. At the end of the day, there's a wide feature set in Splunk in terms of being able to support apps, being able to support single instance deployments, as well as large distributed topologies. And we knew that we wanted the image we built to be production ready and capable of handling all of that workload. Lastly for this is a little bit of autonomy. So we really wanted to think about and reduce the external dependencies we relied on when actually bringing up a full Splunk deployment. At the end of the day, operators should only worry about running Splunk and not things like Zookeeper and etcd with it. On the scheduler side, fault tolerance is a big one for us. We need to think about what happens when pods or containers fail, or when even nodes go away. What happens during the life cycle of a container as it restarts and gets scheduled on different hosts. Statelessness is an interesting one for us as well. We really wanted to draw the line in terms of where state is being managed on the scheduler and where state is being managed on the application. And lastly, the fun one is scalability. So a lot of container orchestration platforms now have a wide set of features to support high availability. These are things like auto discovery of new services, dynamic load balancing, and even auto scaling of your pods and containers themselves. We really wanted to leverage this and port it back and make this whole Splunk enterprise experience in containerized formats to actually utilize all this. So when going back to our Docker file, we actually went back to square one here and decided to split things out into a base platform layer as well as the actual product layer on top of it itself. So we have two products that we ship. There's the Splunk Enterprise as well as a lightweight Splunk Forwarder. And really the impetus for this comes from a lot of what we learned from running Splunk in our own containerized CICD environment. While we're not too opinionated on which operating system gets used and Splunk runs on top of, we found that our end users did have a preference. You might have some QA groups who care about testing against CentOS or some other groups who depend on Debian. At the end of the day, we also wanted to support Windows and Red Hat in the future as well. And this really kind of mapped to what we expected end users or external customers to also want. You might have organizational policies or security demands in place that suggest and lean towards one operating system over another. And by doing this, we really provide that freedom and flexibility for our end users to make that decision themselves. Additionally, fun fact that the Splunk forwarder image also supports different chipsets. So we have one for the x86-64, as well as one for S390X running on Z-Linux. By having that base platform layer as a separation between those two, it really simplifies our build process for that. And we can heavily utilize Docker multi-stage builds for this. Additionally, this is also thinking about the future. So the Splunk that gets shipped today may not necessarily be the same Splunk that gets shipped 3 months from now, or 1 year from now, or even 5 years from now. As more work goes into Splunk Enterprise to decompose it into a more service-oriented and microservice architecture, we wanted to be sure that we could support that path going forward, and we can continue to evolve and grow with it. So at this point, we have Splunk running in our Docker image. We can probably launch it, start the process, have the daemon run in the background, have the web UI accessible. But at the end of the day, it's still very much unusable to our end customers. Because the first thing that you might need to do is actually get data into the platform. And once you ask that question, you really open up a Pandora's box of different options. How do you want to get data in? Do you want to do file monitoring or socket listening? Do you want to receive syslog data or HTTP event data? Maybe this Splunk instance in a container is actually being used to forward data to a separate set of systems entirely. After that, who gets access to the data? How do you set administration privileges and user access control? How do you install licensing, indexes, configurations, apps? Here, the list goes on and on and on for us. So we really wanted to tackle the challenge of versatility. How do we manage the onerous task of application configuration as well as reconfiguration over time? For us, it was really important for us to determine what are the lowest common denominator of tasks that users would need to run in order to make use of their data and ultimately make use of our product. And again, how do we make this an out-of-the-box experience? So what we found is that there was some need for a dynamic configuration layer at boot time to help facilitate this for us. And that's exactly what we went with. We call it the micro-orchestration layer. But in essence, all it is a set of Ansible playbooks that get shipped with our Docker image itself. You can see in a Docker file here, I actually copy the Splunk Ansible playbooks into our image, and we call an entry point that calls the start service. In our entry point script, it's actually responsible for calling the Ansible playbook command. And really what this did for us was really allow a separation of concerns between the container scheduler as well as the application's setup time. It runs asynchronously, so each container, as it starts, it will run its own set of Ansible playbooks to provision itself and join a cluster or provision itself as a standalone. This layer also helps us eliminate the reliance on any third-party services or third-party registrars. We don't need things like Zookeeper and etcd if we can share the context of the application amongst all the members of the cluster itself. Additionally, we also reduce the order dependencies that you might have in terms of bringing up a service. You don't need to bring up service A before service B this time. Everything can come up on its own, and we handle that asynchronous parallelization setup time, and ultimately that results in a faster time to value. Again, we really thought about this in terms of how it would work on different orchestration platforms. We wanted to make sure that it was portable, so it would work on Swarm or Kubernetes. It would work on a production cluster environment, as well as your local developer laptop. So before all the Bash purists out in the crowd start sharpening the pitchforks and lighting the torches, why did we choose Ansible for this? We felt that was a very domain-specific language capable of infrastructure and configuration. It does that really well. More importantly, it really appeals to a lot of developers and operators. In a way, it's very transparent. It's self-documenting with its readability. It also allows us to confront things such as idempotency and graceful failure handling, which is what we would need to do anyways in the future. Again, we also felt that pure Bash by itself had fairly low testability and maintainability. With Ansible, we can actually take advantage of the molecule test framework as well as revert to Python mock testing for any dynamic inventory scripts or library scripts we want to include as well. And you can see here from this example, what I want to do is actually set up a forwarding server. So in Splunk, this just means I want to send all the data from this Splunk instance to a separate one entirely. And you can see it's very complicated. We actually call this command twice in Bash, depending on if you only have one forward server or if you have a list of multiple forward servers. There's a lot of short-form command line arguments. There's a lot of evaling and echoing and escaping just to achieve a pretty straightforward tasks. With Ansible, we can actually condense this down into a short 5-liner. It's much more readable. It's much more friendly to see. And even it's better for new developers who join our team to get familiar with the order of how things are done. Additionally, by providing this common set of approved Ansible playbooks, we hope that this extends beyond the use of just Docker, but it'll help other customers in terms of bringing up the software that we develop into other infrastructure providers. So we hit a lot on the application requirements side. Now let's go back and think about what actually happens on the scheduler and what the scheduler is responsible for. So fault tolerance is a big one. Obviously, you need to think about the cases when your application fails or when your containers fail. Again, if you don't plan to fail, you're failing to plan here. And for us, we really, by having each container bring itself up asynchronously, we're automatically dealing with service disruption and network intermittency at the coding layer itself. And you can see from the example I have here, one of the tasks that we have is actually joining an indexer cluster. We have a lot of retry logic here. We have some delays in between retries. We can even add exit early or break early conditions for us, or fail fast ways so that we can handle these issues with grace. Additionally, we also ship with our own script that runs as a health check. So you can wire this up to your Docker health check or your Kubernetes liveness or readiness probes to handle the actual lifecycle of your container as it runs. The appropriation of state is a big one for us here as well. We really wanted to separate the concerns of what the container scheduler was responsible for, as well as what the application was responsible for. We felt that the scheduler's responsibility was just to bring up the inter-service coordination of all the containers and pods that run, whereas the application's responsibility was more for the intra-service bootstrapping and setup process. So on the orchestration engine side, all it should do is administer the pods and the containers or handle the networking. Meanwhile, the application context is actually shared amongst all the cluster members that are participating in this deployment. And we do this via environment variables. Effectively, we really get the benefit here because by making the application context stateless from the perspective of the scheduler, we can actually make really complex applications simple to manage just by setting the scale of their individual components. And we can kind of see what that looks like in the future. But in this example I have to the right, I have a search tier composed of one search head. I also have an indexing tier composed of two indexers, as well as a cluster master that acts as a broker in between both of them. So we're going to walk through a little bit of a Docker compose of this architecture that I have, of the Splunk deployment that I have to the right. It'll start at the top. We're just going to create a network. The driver here doesn't really matter, but we want to make sure that it's attachable so we can add containers to this particular network. We're going to start by defining that first service, that first search head. So I'm going to add it to the network, give it a little network alias so other containers can reference it. Use that Splunk latest image that we publish. Just for a friendly naming convention, I'm going to give it the same container name, searchhead1. And then in environment variables, you can see that we actually pass in the rest of the topology so that it's known among this particular container. So indexer1 and indexer2 are passed in. The searchhead1 is also passed in to itself. Cluster master 1 is available at the cluster master URL. And the primary difference here for this particular container is we have a Splunk role defined. So the Splunk role here acts as Splunk search head. So when this container brings itself up, the entry point will know to bootstrap itself as a search head and connect it to the various services in this topology. On the cluster master side, you'll see that a lot of this is the same. The entire state of the application of the deployment is passed in. The only difference here is Splunk role is now Splunk cluster master instead of Splunk search head as we saw before. And this will tell this container, I need to run these set of tasks to bring myself up as the cluster master. This gets pretty boring pretty quickly. You'll see that indexer and indexer2 are pretty much identical. Again, the only difference is the Splunk role is Splunk indexer. State of topology is shared amongst all of these pods or all of these containers. So scalability. How do we think about when things scale, or how do we do dynamic auto-scaling for us? For the example I showed before, how do I add a new indexer to the same deployment that I've previously created? So we can actually take a little demo of this, and you can kind of see all the pieces of this coming together and how we bring it to surface. We're going to run a compose file here from our Docker Splunk repository on GitHub. It's the cluster absolute unit scenario. It actually brings up more containers than the previous deployment, but we can walk through that. So I'm going to just run Docker compose up, bring up every container in this cluster absolute unit scenario. It's actually going to be composed of 4 indexers, 1 cluster master, and 3 search heads. As soon as I run this command, I'm going to go inspect the logs for my cluster master. You can see that Ansible is already immediately running at boot time, it's going to set itself up with the default common provisioning that all Splunks would need, as well as start to introduce the cluster master specific roles for this particular container. After this process begins, you can see that it'll finish pretty immediately. We're just going to make sure that Ansible playbook has completed, and then we're going to let the container run and handle the rest of it. After this, I want to make sure that the state of the deployment is ready and available for use. I'm just going to go check what happens when I access Splunk Web of that particular cluster master. Just by logging in, I can actually go visit the indexing cluster dashboard just to see, is all my data available? Have the indexes been replicated? And do I have 4 indexing peers? And in this case, I do. So now we're going to go walk through and actually spin up a different compose file. And this one actually leverages the same Splunk network that we created before, but all it's going to do is just add that single indexer. So when this happens, we're going to just view the logs for that particular indexer again. You're going to see that a lot of common Ansible playbooks are being shared across each. They all have a same set of common provisioning. The only difference here is, again, it's going to join itself to the cluster master because I have that shared context. All right, this is finished. In the background, you may have already noticed that indexer 5 is already joined. I'm actually going to refresh the page just so you guys don't think I'm crazy. And indeed, we do have all the data searchable, search factors met, and 5 indexers registered properly. All right, I'm going to pass it back to Tony to go over the results of what we've done and see how it's being used out in the wild.
Thank you. Pretty magical, right? The demo we saw, we made it seem easy, but in a complex topology, it used to be something that our support engineer has to be on the field to, loop those clusters together. But anyways, let's talk about how we've been using these approaches to solve our problem. So we actually took this to open source and release it to our customers so they can deploy Splunk in a containerized environment. So the code, all the code is on GitHub, and we've been seeing a lot of feedback and response from the open source community. And obviously, the loop of our support is a lot faster on just replying to the issues on GitHub than to go through the kind of official corporate support channel. And we also include examples for Swarm and Kubernetes. So Docker Compose or Manifest for Kubernetes, those our customers can take it and just use it right away. So this is a snippet of how many issues we're getting on GitHub. And then we are able to address our customers' problems right away on GitHub because it's an open source project. Internal usage is a little bit more complicated. Our customers are focused on having one kind of Splunk cluster running and keep it running in their infrastructure. We have more diverse usages. So we eat the same dog food that we sell. So the open source code is also fed into the internal pipeline to use the same containers that we ship internally. So for dev and QA, we need a kind of repeatable and ephemeral need for containers so we can deploy the code changes and every build and run the test and tear it down and so on. Sales, more focused on kind of providing a reliable demo, official Splunk product, demos to the customers. And for support, we need to replicate customers' data and customers' environment. So taking the same version and the environment that the customer is running, deploying it internally to our infrastructure is a good usage of support. So we have to meet all these needs from different departments internally. And this is a very high level of how we do clustering or infrastructure management inside of Splunk. So we rely on UCP, which is a universal control plane, a product by Docker, which is a kind of management layer on top of either Swarm or Kubernetes. So we have multiple clusters of container orchestration layer inside of Splunk. And then we were able to separate it by teams and also by usages, right? So maybe dev and QA sales team need a Windows container and Linux containers. So we are able to mix up Windows and Linux containers inside of that cluster and let those teams use it. On the other hand, support team might have customer data, and then it gets into what kind of environment you need. So maybe you don't need a Windows container in that case. Then we have a separate cluster for that usage as well. So we also automated spinning up the clusters very easily inside, so we can spin up different clusters with different environments internally for diverse use cases. One thing I forgot to mention is a tool called Orca. So it's great. We have all this clusters, UCP clusters set up, Kubernetes set up, all of that. But how do engineers actually put their containers onto that orchestration layer? So we have a tool called Orca, which is an in-house developed tool, which is a command line tool for deploying different containers onto different clusters. So you can pick and choose, this is the cluster I want to deploy to, and this is a container I want to deploy to, and these are the configurations that I want to apply to these containers. So Orca is able to automate and deploy different versions of Splunk, different topology, and it doesn't even have to be Splunk container, right? It can be Hadoop, or it can be Mongo. If you need any other containers, we can handle that for you. So Orca has been the backbone of serving all these needs internally. So this is a quick demo of how Orca works. It's super quick, so let's see. That's it. In real life, there's a little bit of loading because it takes time to provision a container. Oops. Okay, let me replay that. But anyways, Orca create, I'm telling it to just give me a single standalone Splunk and deploy it to the default UCP cluster we have. And then you saw that the log output was, here is the name of the container, here is the port mapping to the web side of the Splunk instance, and this is what we're looking at. All the data is indexable and it's configured and it's set up, ready to go. So it takes about like 45 to 50 seconds to spin up and configure one Splunk container. As I mentioned, we also heavily utilize the UCP. So this is what UCP looks like for us. And our scale is pretty massive. We deploy, on a bad day, we deploy about more than 50K containers per day to this cluster, and then on a hot days, we deploy more than 100K containers to a single cluster. So you can see that we are able to look up containers, see how it's provisioned. So it's a good kind of management layer on top of Swarm or either Kubernetes. So it's great. We are able to meet the demands of different organizations or different customers, but how do we take care of this internally, right? So let's talk about the CICD a little bit. Obviously, we have a need to support multiple platforms and multiple chipsets. We need to run security scanning on every single build we put it out there, functional tests as well, and also we need to do version control. So Splunk, version X is going out, what happens to version Y? So it's a replication of work that happens to subsequent versions. So very high level pipeline of how we do this internally. So as I mentioned, all the code is on GitHub, all the development and the customer requests, all those are addressed on GitHub. And the code change is pushed, the pull request is made, and then what happens is Circle CI is running to build a container with the code change, run the security scan using the Claire scanner, run tests that we have with PyTest, and also the Ansible test, and then the code is blocked until all the tests are passing. After the test passes, it kind of it merges onto GitHub, and then we have our internal Jenkins pipeline that fetches the GitHub code and then builds internally. The important thing is that we are able to parallelize these builds across multiple platforms. As you can see, we have IBM S390X agent and Linux agent, and we have Windows agent, and so on and so on. And those will be all building respective containers to their environment. And then those built images are pushed to the internal registry, so it can be consumed internally by different teams, and also pushed to Docker Hub for our official release of Splunk containers. So the future, where do we see this journey going, right? We've been focusing on how to deploy and configure Splunk. We haven't been really focusing on how to manage it and how to keep it alive. So deployment frameworks such as Helm or operators are the paths we're looking into to make sure our job doesn't end at just deploying and configuring Splunk. It is an ongoing, it's a long-living instances. You want to keep your service alive, so we want to help our customers also manage these containers as well. We also want to find more common denominators, so we can extract out the configurations that customers use for Splunk and automate it, right? So, and also we want to keep looking at the future of monolithic software, right? The goal is not to get rid of monolithic software on day one. It's more of making a bridge to the next step, because your monolithic software, if your company was built on a monolithic software, that's the one that brings cash into the business, right? So in summary, we found ways to bridge the gap while migrating from monolithic software to microservice architecture. You always have to plan for the future. It's okay if you started your business on a monolithic software and you want to do the crossover. You just have to plan for it. It doesn't happen in a couple of days. It's a long process. And there's no single answer. So when we were putting Ansible into the entry point, we got feedback saying it's more of an anti-pattern, unconventional use of containers, because it's most of the examples and use cases tailored to, hey, just run this server, or a single command for the entry point, right? But we are actually running different cycles of scripts and provisioning inside of our entry point. So it's like similar to how we are extending the boot up time of a container, but we were able to achieve a lot at the boot time for dynamically. So there's no single answer. Dynamic self-orchestration made our software offering more nimble, and that's what fits our case. And if you're looking to solve your problem, don't be afraid to go anti-pattern sometimes. Whatever it takes to get the problem solved in an efficient way is your answer. So, beautiful thing, that single command of Docker run command, if you have a Docker engine running, you can get Splunk, a single instance of Splunk set up and running in less than a minute and a half, assuming you have a good network connection to pull the image. So this is how we made Splunk usable and more easily usable by our customers. And we also have links to repositories. Those are open source GitHub repositories of our work, and documentation as well. We have a user group on Slack, and our email's on there. So if you need us, we are reachable. That's all I have today. And we can accept questions then.
Sounds great. Thanks, Tony and Nelson. Thank you. This is great. This is very pragmatic. Nice way of looking at it. So I'm Pab. I'm going to be a moderator. I'm a Docker captain. So any questions? I want to see it back there. Anybody has questions for Tony right now? Or Nelson?
Sorry, question in the front.
Hi, has this switch actually improved your developer productivity?
Yeah, I would say absolutely. Previously, a lot of the developer workflows were running Splunk on VMs and of sorts, right? At the same time, when running Splunk on VMs, the teams have to manage those VMs. They have to control the dependency layer for those. Having things like the containers for us really simplified the whole setup and deployment of those Splunk containers and the Splunk services. We make a lot of it disposable and ephemeral, and that really frees the developers' minds to actually get their changes in, test things quickly, see what it looks like, and iterate a lot quicker in terms of that dev loop cycle.
Okay.
What portion of your customer base deploys on Docker?
So the question is, what portion of our customers deploy Splunk on Docker? I think the general trend is moving towards taking a software that you use, put it into a container, and just throw it into an orchestration layer such as Kubernetes, right? So Splunk, so traditional case has been customers kind of download the binaries, they spin a bunch of VMs and install it and configure it, and then they're able to say, hey, put all my application logs or business logs ported over to the Splunk instance. That's been a traditional way of using Splunk. But now with this trend, people just take the Docker containers, deploy to their Kubernetes cluster or something like that, and just start using. So the short answer is that everyone who's hosting Splunk on their own data center can just take this and deploy it and start using it.
Oh, go.
Hi, you just mentioned that customers can simply download and run that on the top of Kubernetes. You are a product and you convert that as a portable product. So is it really required to run, or it's a mandate that I have to run with Kubernetes, or if simple Docker engine I have it, can I put on top of it and will it run your product as of now? Without Kubernetes, is it possible?
Sorry, could you repeat the question again?
Yeah, now I just saw you containerized your product as a portable one, and you are running on top of Kubernetes. Is it Kubernetes cluster is a mandate, or can I run it on a Docker engine, like a Docker?
No, it's not a mandate. As long as you have a Docker engine, you should be able to use these containers. Kubernetes just helps you manage the distributed environment.
Thanks
Yeah.
for that.
Again, we wanted to make sure it was capable of running on both Swarm and Kubernetes, right? The image should be agnostic to the scheduler. We don't really want to pin ourselves to the constructs of the implementation of how it's done on specific engines.
Makes sense. Any other questions? I think we're coming to the end of the session right now. I believe Tony and Nelson are willing to stay a little longer if needed. I'm not sure if anyone else has it. Oh, one over here.
We'll also be staying for a while, so please come up and ask questions.